And again, I would talk to like a professor in English or a professor of languages, you know, if you want to learn more about shibboleths, because I'm a professor of computer science and I only dabble in that kind of stuff occasionally. Okay. So let's go to, so I did not get the chance to update what I wanted for this exercise, so I will just tell you all manually what it is. So first off, remember, watch the Big O videos. So first off, I know that some of you have been or are currently learning about Big O notation and runtime analysis, okay? You learned about that in like what, 10, was it 1033? What is the class for math concepts and computing? 2166. There's 1166 and 2166. That's it. Okay. So you probably learned about that kind of analysis in one class. They are much more focused on the formal analysis of it and basically what it means and how that like compares to other things. For here, we're more focused on what that feels like, what that basically what happened, like literally seeing what happens if we increase the input size of the thing that we're working on. So if I increase the input size of the list by 10, basically if I go from 10 items to 100 items, what does that do to the runtime? Does it mean it's 10 times longer or 100 times longer? Or does it just not change? That's the kind of questions we're asking. So for this particular class, right now, we will be focusing on a grand total of 5 runtimes. We are dealing with the first 3 right now, which are constant time algorithms, linear time algorithms, and quadratic algorithms. Those are runtimes. Linear, so constant time, O(n) and O(n) squared for the most part. Those are what we're going to be dealing with. When we get to trees, we will be looking at n log n and O(n), because the way it typically works is that we see what an O log n operation looks like, and then you do n of those, so you get n log n algorithms. That's how we get those. Also, those of you there may be a lot of you who are like terrified of the notion of logarithmic of that, when you see the log symbol, it's kind of complicated and looks stuff. Again, I'm much more focused on a utilitarian kind of a view of mathematics and that kind of stuff, because this is more of a utilitarian class. On a theory, we don't need to delve heavily into the math theory. That's other classes cover that, so I don't need to. So as a result, I can tell you that the logarithmic operation is just basically counting the number of times you can split a pile, and which I go into more detail at when we get to logarithms. But it is much easier to kind of figure out what logarithms are when you think of it in terms of pile splitting, as opposed to a relationship between exponents. All right. So for the most part, I go over some algorithms. There are some other complexities that you will be looking at. So let me go ahead and open up the assignment page. And go over it with you. So this is not a programming assignment. It is a math assignment, kind of, sort of. Close enough to a math assignment. Okay. It's a PDF. I revised it for my graduate students who do basically the same thing. So that's why it says 5016 on it. But honestly, don't be put off by the fact that I revised it for the graduate students. It's the same thing. So first off, there's some rules here for basically saying T of n. T of n is basically saying this is the amount of time it takes for the algorithm to run. But we don't really know what the exact time it is, so that's why we use Big O notation. It kind of gives us an order of magnitude. And the reason we don't know exactly how long it's going to take is because your computer doesn't necessarily follow your directions, because it's got a million other things going on. It's not going to just do all the process all at once. It's got to make time for like moving the mouse and waiting for user input and that kind of stuff, and dealing with other programs that are also running. So the first 10 problems are dealing with simplifying these T of n's to their Big O time. And the two rules for doing that are over here. So basically, we only care about the biggest order of magnitude. Again, if this confuses you, watch the videos. We only care about the biggest order of magnitude. So over here, right, as n gets big, and when I say big, I mean really freaking big. I'm talking maybe 100 to the 100th, okay, power. When it gets that big, the NQ factor completely dominates these two factors over here. These don't matter anymore. When n gets really big, the other factors just don't matter. They essentially end up as error. Like a little bit of, they don't provide any significant figures. Okay, constant factors don't matter. In other words, it doesn't matter. There's no difference between T of n is equal to 500n or 5,000th of an n. They're both O of n. They're both linear. They have a linear relationship. So we just say O of n. Okay. Now, when you're optimizing, obviously you want the smaller constant, but when we're trying to just figure out, okay, what's our algorithm, then we just care about the order of magnitude. Okay. So also, how do you turn this in? Don't care. I don't care how you turn it in. You can do a notepad full, a text file or a Word file full of answers. You can open this up and edit it in Word, or you can edit, or you can write on top of the PDF, print it out, or you can submit it to me, or you can just, electronically upload your answers online. I really don't care so long as you're turning in the answers. However you do that, and is all that I care about is that's the easiest way that, one, it works for you, and two, I can actually, see, okay, there's answers here. Okay. So the first 10 are simplifying this. Now here, 3 and 4, I'm trolling you. 3 and 4 aren't what you think they would be unless you've taken calculus 2 and dealt with infinite series or converging series, in which case they're exactly what you think they're going to be. So I will go over those on Thursday to make sure that you get those. Okay. So don't worry about those. Just try your best bet at it, or just Google the sequence 1 + 2 + 3 ... Okay, try Googling those sequences and see what they come up to. Google's your friend here. Okay, here these are questions about array lists and how long those operations take on array lists, and then question about explaining why that does that. So 17 and 18 deal with the puzzle, which I have, which is found on the back because of rendering things. This is from a puzzle book I really liked as a kid, where basically it was a maps and mazes kind of bunch of puzzles that were all revolving around maps and mazes. Okay, so basically it's asking some questions about this and graph theory, and then paths. So the only thing is that I poorly worded question 18, so I need to send an announcement amending that, which is that I say let the number of stars be defined as n if there are n stars and a line between every possible pair of stars. And that is my mistake, because that changes it to be way too ambiguous. Instead, I want it to be a line between, a line between every possible pair of, if there are n stars and a random number of connections between stars. So lines between stars are randomly distributed, but you are guaranteed a path to the end. Okay. You're guaranteed that it's still a graph, in other words, and not two graphs. How many paths would the algorithm need to check in order to find the solution? All right. And then finally, because we are dealing with algorithm analysis, I get to use one of the two algorithms that exist specifically for algorithm analysis. You will never use these outside of a classroom because they're terrible. They're terrible. They exist for the purpose of analysis only. BOGO sort is sorting by shuffling. Essentially, what you do is imagine trying to sort a deck of cards by throwing the deck of cards in the air, then picking up all the cards at random, and then checking to see if it's sorted. And then you repeat that until you actually end up with a sorted pile of cards. That's BOGO sort. Basically, we are just simply doing stuff at random until it works. If you're in doubt, please look for the worst case run. Look it up on. You can check Wikipedia. And then there's a difference between the worst case and the average case. And then finally, question 23 is for the methods you wrote in lab 2, figure out the time complexity of the method you wrote. So I'll make an announcement to adjust question 18. Okay, so that one is corrected. But again, this is kind of hopefully this should be a bit of an easier week. Now, what about how does this work with demoing? Well, you still demo it because because I find it. So this is for me, what, like 40 people in this classroom, not in this classroom, but like registered for this class. I've got a bunch of people who are currently in the Zoom room today. But you know, when you're dealing with 200 students, you can't necessarily go to each of them and tell them what they did wrong and tell them to go fix it. But that's what but I have less students than that, and I have the luxury of the lecture being set up the way it is. So if you get when you demo it, I'll show you what you got wrong, tell you to go and fix it, and then you go and fix it so that you can get 100 on the assignment. So it's not like a normal, so it's not like a typical math assignment where I'm just going to hand it back and just put an X through it, and you go K, because that's not a useful learning experience. All right. Lastly, our first exam will be week 6. This is currently week 3. Okay. It will probably be week 6 on Tuesday. That is probably when we'll do it. Wait, no, we do it on, is it going to be week 5? No, we do it in this lab. So it might be week 5 on Friday. I'll check. It'll either be week 5 or week 6. Okay. This is week 3. You will get a practice exam. Okay. So don't worry. So you don't have to worry about having an exam next week, but just depending on where the class is in terms of linked list, that's going to dictate when I give the exam, because the exam primarily tests you on array lists and linked lists. Yes.
Is this lab 2 next Tuesday?
Did I not set a due date? Boo. That sounds like a great time to have this due. I knew I forgot to do something. Went through and did all the other assignments for due dates for, assignments in the other classes, but neglected this one because I'm like, it's 2168. I do that one. That's fine. All right. All right. So that is essentially it. So go ahead and you could go ahead and get started on that. You can continue working on last week's homework, or you can start working on this week's homework. Or you can demo. I'm going to check in with the people on Zoom first, and then I will start making my way around. Okay, give me 1 second to stop recording here, because